Hi, it's Terry Denery of the MathWorks. So anyways, let's continue with this model that we just created, essentially using our tool SimWise to very efficiently, quickly, and accurately put together the four-bar linkage that we want to work with, all right? And then bring it into Simulink. And there's this great value of bringing it into Simulink because you can begin to integrate all the parts, the electric motors, the controls, and have a path to hardware because you can generate code that will run on the relevant embedded processors. So anyways, this is where we kind of finished off last time. Run that again. So just rewind in that very simple motion, right? So the torque required to do that, that's provided by our motor that's going to be located right where my mouse is, right there at the center, right? And that based on what that four-bar linkage is, and it's pretty small. It's like that big. Its primary biggest dimension actually I think was 0.25. So let's say about a quarter of a meter. Okay, 0.25 meters. So it's based on you know how much those parts weigh, how that mass is distributed through the shape of the part, but it's also dependent on how we're moving it. And the faster that we want to move it, and more specifically, the faster we want to accelerate it, the more torque required to do that. And of course, we got gravity acting in this, and that's why it's just essential to have a good mechanical simulation tool so you can understand these things, right? So we're in the world of Simulink now. The design of this, I'll call it export, was to create some interfaces to motors. And so we see how we can send in torque or motion. The other thing we can do is we can make some good measurements. And so this output port right here is what they call a bus. And what I like about buses is that it's all this relevant information by names that you're familiar with. All right, and so I'm going to just delete that. And with regard to the purpose of this video, which is to show how you select the appropriate motor, um, turns out torque and speed are kind of your key things. And torque and speed imply power. So if you are a power person, certainly, that what I'm showing I think kind of fits into that too. But anyways, let's measure both torque and speed. Select those. Okay, those are now outputs from this block right here. Let's send those into a scope. All right. I like this. Notice when I click on this, it tells you that that's your torque signal. When I click on this, it tells you that that's your speed signal. All right, and so let's just rerun this simulation, watching it. And let's put this into two separate measurements. And with those signals labeled, they'll even transmit that to the plot. So our top figure is torque. We see its maximum, and I think this is very important. It's an absolute value because measurement of torque in general is kind of dependent on what your reference frame is. So plus negative, I think it's kind of a clear point, um, is a somewhat arbitrary uh, characteristic based on how you chose to make that measurement. But anyways, maximum value is about 0.3 Newton meters, and then the maximum velocity is, this is degrees, about 170 degrees per second. And I think what I'm going to do, I think this is kind of a relevant point. Kind of make this big enough. Let's put a gain in there. And let's get the units to be consistent with how we've been doing motors already, right? And I'm going to double click on this. And converting from from degrees to radians. It's simply a multiplication of pi divided by 180. Again, a tool like Simulink is just kind of great because all that stuff is so available for you. Okay, and so anyways, let's run it one more time. And so we'll see that whatever it was, 160, 170 degrees per second translates to about 2.5 radians per second. And so, the basic idea of sizing a motor, and I'm going to go to our original model as we kind of moved into this mechanical piece, is the way that we define our motor, right? And it took me, I've been at MathWorks now 16 years. It probably took me like 14 of those years to really understand why this is so important. Okay. And so we saw how I did this before, and I'll simply kind of state it clearly. If you're going to buy a motor and the process is usually it's go online now and interface with essentially these motor catalogs, and they're just going to give you a big list of probably like 100 motors, and you choose based on your requirements, and that your requirements expressed are going to be in terms of voltage rating, stall torque, no load speed, and in general, you simply kind of allow the inductance choice to be dictated by what's available in their catalogs. And I think number of pole pairs would probably fit that too. Okay. But anyways, at this point, we're pretty close to done. All right. Because we know what our maximum torque is, which is the same thing as stall torque. Well, let me be careful about that. Okay. Our maximum torque is occurring actually while it's moving. All right. And therefore the stall torque required to produce that will be bigger. All right. And but let me get back to the point that we do know what our maximum torques are and our maximum speeds. And I'd say at this point, there's a little bit of trial and error, but what's a better tool than a tool like Simulink, which allows you to put in these numbers and to essentially, you know, um, see if it'll work or not. Is the power of this motor really enough? Okay, so anyways, I think we're covered pretty well, and certainly, we use those numbers. We said, oh, okay, zero point 0.3 on torque. Well, I think a value of 1 should be good enough, and a no load speed of 4 times what our maximum speed is. That seems like it'll be good enough. And we hit run, and we saw that we did not get excessive voltages, we did not get excessive currents, and that in general, we came up with a system that worked. So why don't we just go ahead and prove that to ourselves one more time, and we will run this model and wait for it. And it's a different model because it's showing it from the different direction. Okay, and anyways, we kind of observe and we see that everything looks good. So kind of a simple video, but critically important. Choosing the right motor is how you make sure you have this thing that I would call the perfect torque generator. And that's the combination of motor plus controls interfacing through power electronics, the electric drive. Thank you.